So thank you very much. I'm very happy to be here in person to present you this work that we did a few years ago, and want to again thanks the organizer for the opportunity to be here. And so the work that I'm presenting today is about a novel point of view on the static analysis of ReLU neural networks using abstract computation, but based on tropical geometry, on tropical polyhedra. Yep, this is working. Okay. So what we analyze is ReLU neural networks, that is the particular feedforward neural nets made up of linear layers followed by ReLU layers, in which you apply pointwise this nonlinear activation function, that is the max x 0. So we focus on this kind of networks, and our static analysis will allow us to get over approximation on the ranges of all the neurons, and this can be used to prove some specifications. So usually when I present this work, people often ask what kind of specification can we want? And I mean, it's a very good question, because often we use neural networks in cases in which we don't have a full specification of what we want the network to achieve. Nevertheless, there are cases in which we know what we want, we have some specification. But perhaps more interestingly, more importantly, there are many cases in which we want the network to be well behaved in a particular way, depending on the applications. One of the ways you might want the network to be well behaved is related to this panda that you've seen already multiple times this week. That is, you want to prove that you don't have any adversarial examples. Like if you start from a panda and you move only a little bit, you want the network to still believe that it is a panda. And this is amenable to set-based analysis, because you can take just a small box around the panda, propagate it through the network, and you want to check that you are still in a small box in the output layer. So you can do this kind of things, and it has been done before with like complete techniques, but that are not really scalable. And another thing that has been done is to use abstract computation, which is really great, but usual domains, that is numerical domains that are based on convex shapes, have trouble when they want to deal with the ReLU layers, because well, those ReLU layers are non-linear, non-convex, and so you have two options. Either you make an over-approximation for those ReLU layers, but then you lose a lot of precision. Another thing that you could do is to do some sort of disjunctive analysis, some reasoning by cases, but well, then obviously, very quickly, you're going to have a combinatorial explosion, and this doesn't scale. So what we propose in this work is to design an abstract domain that deals with the main difficulty that those other domains have, that is to deal with this ReLU layer. So for that, we go into the world of tropical geometry. And the world of tropical geometry is a world in which the maps operation is very easy to deal with, which is perfect for ReLU layers. And actually, it's quite natural to go into this world if you want to analyze ReLU networks, because well, if you look at the kind of things that ReLU networks compute, you can see everything in a tropical geometry point of view. Like the decision boundaries, they have some sort of tropical shape. The thing that they actually compute, well, you can see it as a tropical rational function, and then you have a neat way to turn that into, to approximate that by a tropical polynomial or by a tropical linear function. So this is what we do. But so to tell again what is tropical arithmetic that we use in this work, it's when you work with real numbers like you are used to, but you replace the addition by the max operation, and you replace the classical multiplication by the plus operation. And when you do that, you can compute mostly like you are used to. but you don't have any inverse for addition. You only have a summary. But anyway, things still go well. You can still define geometric objects in the same way as you are used to do it. So you can define tropical half spaces, just like you will define classical half space. So a typical half space would be the set of x, such that this sum of ai xi plus c is smaller than the sum of bi xi plus d. But you replace the plus by the max and the times by the plus. And when you do this in R2, you get this kind of shapes, like in blue and red. Those are tropical half spaces. And if you look at the graph of the ReLU function that we are interested in, well, it's just a particular example of a tropical segment. And it's also a tropical polyhedron that is an intersection of tropical half spaces. And this is good because it means that using the tropical polyhedron, when we want to abstract the ReLU layer, well, actually, we are going to be exact on this. But then if we use convex domains like polyhedra or zones, then we're going to lose some precision and have to add the gray shapes. So I'm not going to go into too much detail about how we represent our tropical polyhedra, but it's like classical polyhedra. We have an internal and an external representation. We can represent them so externally using constraints, so as a conjunction of tropical half spaces, or we can represent them externally, internally, I mean, sorry, as the tropical convex combination of generators and extreme points, and we can convert between the two, but it's quite expensive. And for the rest of this talk, what you can keep in mind is that tropical polyhedra are particular unions of zones, and where zones are those shapes that are more common in abstract computation and model checking. So those particular polytopes that are made of faces at 0 or 45 degrees with respect to the Cartesian axis. And so in a way, tropical polyhedra are a compact way to represent union of zones. Not all union of zones, but some of them. And so it allows you to do a little bit of disjunctive analysis. And this will be useful later, but we also have relationships between tropical polyhedra and zones. We have a way to compute the most precise zone that contains a tropical polyhedron. And we can go from zones to an equivalent tropical polyhedron, both in internal and external representation, with everything being closed form. It's very fast to compute if we need it. Right. So I told you what tropical polyhedra are and why we want to use them. But no, let's actually use them to do abstract computation. So we want to do abstract computation on ReLU neural networks. So we are going to need a few operations. We are going to need transfer functions for the ReLU layers, for the linear layers. It will be convenient for us to have joins, meets, some conversions. And at the end, we want to actually prove some property that will be given to us as an affine inequality. So we want, in order to prove this property on the tropical polyhedron, we also want to test, I guess, affine guards. And I'll talk again about that in the end. But first, for the ReLU layers, everything is simple, everything is exact, and I mean, that's the reason we choose this domain. For join, meet, conversions, we have some things that already exist because work has been done before on using tropical polyhedra for abstract computation. So we can use this. The thing is, for us, we have a difficulty with the linear layers. We have to actually do an approximation on those layers. So in a way, we approach the problem from the opposite end as what other domains do, because usually linear layers are reasonably simple and ReLU layers are quite hard. For us, ReLU layers are trivial, but we have a problem on the linear layer. And the reason is that if you look at classical affine function like this, like f of x is lambda x plus b, Well, this multiplication, this lambda x, it doesn't really exist in our tropical arithmetic. It's something that is a bit like x to the power lambda. And we don't have this, so we have to do some abstraction. And well, here, in this very introductory work on the subject, we have not actually computed the best abstraction directly from tropical polyhedra to tropical polyhedra of linear layers, but we just use the best zone abstraction, and we can then convert back and forth tropical polyhedron. So if we want the best zone that contains the graph of linear functions, well, we get this kind of things in dimension 1 and 2. And you can see that when lambda is going to be close from 0 or from 1, we are going to be very precise. But then when we get further, we lose some precision. And actually, it becomes very bad when lambda is smaller than 0, because since we use zones, we don't have negative slopes. And so the best approximation that we have of the graph on the left is just a box. And so we have no relational information between the input and the output. So okay, this is bad. We have some fixes for all of that. So first, I tell you that we go from zones to zones. And you can think, okay, why do you care about using tropical polyhedron? You just use zones, which is a good remark. But I told you that with tropical polyhedra, you can work with unions of zones. So this is actually what we do. Rather than going straight from a zone to a zone, you can start from a union of zones. You do a subdivision into very small, actually, hypercubes. Then you apply the linear layer on all of them. You get a union of zones. And this union of zones, you can over-approximate it rather precisely by a tropical polyhedron. And then you get this kind of shapes that are more precise than what we had before. And it's actually very, well, reasonably cheap to do this subdivision. Another thing that we can do is to try to work on the problem that we don't have negative slopes. For that, what you can try to do is to actually refine the domain to work with shapes that are more expressive than tropical polyhedra. So tropical polyhedra are made of zones. You can try to make something made of octagons, and then we will have those negative slopes. So we do this in the paper, and there's more detail about it. One intuition is that we were working with linear things, so we only add monomials like x to the power 0 and x to the power 1. When we do this, we add x to the power -1. And we could actually try to go working with higher degrees. We would have like semi-algebraic tropical varieties, so more expressive shapes, and just those tropical polyhedra. For that, we can use a tropical Grobner basis, and that's stuff for future work. There's more in the paper about it. But you don't have to look at the details here. But basically, with what we have done, we now have closed form formulas for the linear, for the abstraction of the linear layer, working with both external and internal representation of the tropical polyhedron. And since we have that, it's actually reasonably efficient to compute those layers. Now, to illustrate a little bit our analysis on an example, let's look at a very, very simple neural networks with only one layer, one linear and one ReLU layer. We start with only two inputs, x, that are in a square, from -1 to 1. Then we apply the linear layer, so we turn a little bit the square, we move it, and we get to the hidden layer in h. And then we apply the ReLU layer, and we get y. So if we look at the exact ranges that we see, when we start from this square in x, then after turning it with the linear layer, we get to the pink square on the left in h. And then when we apply the ReLU layer, we get the blue shape on the right. And those are the exact ranges this is the most precise thing we could hope to get. And if you look a little bit more to the right, we get the relationship between the first input and the first output. So now let's imagine that we want to check a few properties about this network. First, we have P1, which is a classification property. We want to check that Y2 will always be bigger than Y1. And this is true here because we are higher than the diagonal. And for P2, we might want to check a robustness property. So if the first input is very small, we want to check that the first output will never be too big. So we want to make sure that we will never touch this red box here. And this is true here also in the exact. But then what happens if we do analysis with something like zones? Well, you see that we cannot hope to prove the second property because the convexification of the exact shape in blue, the second image here, already touches the red box. So with zones, it's not going to work. But if we use tropical polyhedron, even non-subdivided, so just working with zones, but with this additional tropical aspect, we will get the things on the first two pictures. And well, you see that we are able to prove the second property and the first property as well, because we are higher than the diagonal. So we have gotten like first the pink shape and the blue ReLU layer. However, we are not exact. The size of the first shape in blue is actually 2.5 times bigger than the exact shape. If we want to be more precise, we can use subdivisions. And in this case, we get the things on the right, and we get closer and closer from the exact shape. So there actually are a few problems with this as well that are solved when we go with those max plus minus polyhedra. That's more in the paper. And yeah, here you see again this idea of polyhedra as unions of zones. We also have a little bit more in the paper about what we do for multi-layer neural networks. And again, this is quite introductory. So basically what we do is, okay, you start by analyzing the first layer. And then when you want to go to the second layer, we start by doing a very coarse approximation. We over-approximate the output of the first layer by a box, and we feed that to the second layer. And of course, here we lose a lot of precision, but to get back some precision, one thing that you can do is to intersect the tropical polyhedron that represents the input-output relation of the first layer with the tropical polyhedron that represents the input-output relation of the second layer. And when you do that, you get back some of the relationships between input of the network and output of the network. And so, well, eventually we get to the end of the analysis, and then we have a big tropical polyhedron that represents relationships between the neurons, and we want to check some property defined as an affine function. It's a classical affine function, not a tropical one. So we have to find what we can do. One solution, one thing that can be done in polynomial time actually, is to again do a zone abstraction of the tropical polyhedron. And then we use linear programming, and we can check what we want. But of course, here there's a big abstraction. Another thing that we could do is to use the full power of the tropical polyhedron, encode it as a mixed integer linear programming problem. And then we can prove what we want, but it's more expensive. So more work that is needed here as well. And finally, in the paper, there's some ideas about how to tackle the curse of dimensionality problem. So of course, when we use the double representation, it's going to be very expensive and we blow up very quickly. But if we manage to use only one of the representation, so if we can stay on the internal side, try to avoid doing intersections, then we can go further up to a few hundred neurons. And well, there's discussion in the paper about what internal representation is good for. It's quite good for unions. It's quite good for subdivisions. And well, now to conclude, so in this work we've introduced a new point of view on the analysis of ReLU neural networks. So we believe there's many more things that have to be done, but it's worth exploring this line. One of the future work to do is to work not only with those linear tropical functions, but with polynomials. And we also have a lot of open problems. So we have to think about the double representation for tropical polyhedra, because it's not as explored as the classical case. And for a more deeper, more general question, I think it's interesting to explore how we can use the tropical world more generally for non-convex and disjunctive analysis in a clean way. And well, I thank you for your attention, and I will be very happy to answer any questions.
Okay, that's Stephen.
So how do we compare the cost of these transformers to the other options that we have? For example, say zonal loops. So what's the comparison of cost of those transformers? Say, for example, a fine transformer.
Yeah. Yeah, we have not made experiments to compare it directly with the notebooks.
Yeah, not empirically, but just theoretically. Is it more costly? So, for example, you can compute linear transformer with zonal loops in linear time in terms of number of neurons. So, is it linear or quadratic, or is it that sort of theoretical?
Are you asking about the cost of the linear?
Yeah, affine layer and the linear.
Yeah, if you stay on the internal representation and you apply the full pipeline, you will get something that is less than a cubic in the number of neurons. But as soon as you want to switch between the two representations to get back some precision, the intersection, something, this is going to be costly. And well, also at the moment where you want to check the properties, if you use linear programming, you still have something that is polynomial. But yeah, those are the parts that are actually our bottlenecks at the moment. And the rest of the pipeline is reasonably efficient, cubic. I don't know if that answers your question.
Yeah.
Question?
Excellent talk. Maybe I missed it in the presentation. Is your implementation ready to produce?
I must admit that I'm not sure. I remember that we did send it as an artifact, or we tried to. I don't know if it is online. I will try to make sure that we put it on GitHub, and so you can check it.
Thanks.
So you mentioned that that you can compute the optimal zones after applying a linear assignment.
Yep.
What is the algorithm for this?
Oh. It's basically we computed closed form formulas for this, where you have a constant like delta C, these kind of things that are somewhere in the paper. The way we defined it is we pose the problem of what would be the best zone for this. We minimize the constraints, like we make an optimization problem, we solve it, and this gets the closed form formula, and we just do a pre-computation when we get there of those constants, and we throw them there.
Like some kind of LP formulation. Do you use some LP?
No, I mean, yes, on paper, but we don't ask a computer to solve the LP problem. We solve it ourselves in a general case, and then we have closed form formula, and you see like those delta, those C, those are just sums over the parameters.
Because like all these numerical program analysis, they have these octagon zones being implemented, but they never implement the best transformer. They just compute some working practical transformer. Curious if you have actually like an algorithm for computing the best transformer for octagon zone.
For octagons?
That would be the
Very few.
No, for
I know that you can like do something with like LP solving, but that's not very efficient.
Well, I mean, zones are simple enough and linear transformation are simple enough that a human can solve it in the general case. And well, I mean, this is what we do, like to check the proofs in the paper. And
But maybe you are assuming that like you have a non-invertible assignment, why you could actually see.
You have a what, sorry?
Are you assuming you have some kind of static single assignment kind of thing where a given variable only appears once in the set of assignments? So if you have something like y is equal to y minus x compared to y is equal to x plus c, can you handle both cases?
I'm not sure I understand the question. Are you talking about the cases like more general than doing a linear transformation? Or?
No, I'm just talking about linear transformation, but there are two types of assignments, right?
Yeah.
You can assign to the same variable, or you can assign y a different.
Oh yeah, okay. Yeah, I see your problem. Yeah, I don't know straight off my head how to solve it. So.
Okay. Thank you.
More questions? And just one note observation.
Yeah.
You mentioned the double representation.
Yeah.
And that's an issue sometimes in medical analysis.
Mm-hmm.
How do you plan to treat this? Because if you simply consider both domains as not featured, are there ideas for treating a double representation in a efficient way?
What we try to do to be more efficient is to stay as long as possible on only one side.
Yeah.
But yeah, then as we gained some precision some efficiency by doing that. Like from the first experiments where we had both representation, and then we tried doing only internal and using external, very small few moments. It was a bit more efficient, but.
Can you predict this in the analysis of the analysis?
When you are going to need to...
Yeah, to fetch closer to you the right domain.
In our case,
it's just,
in our case, yes, because it's deterministic. It's when we do the intersection to get back some precision, we have to switch, and that's the only place where we have to do it. But it's quite expensive, and so yeah, like being smarter about how we do it will be a great improvement.
Okay, thanks. Listeners, we are perfectly in time. Thanks, speaker again, and the session is